Hello folks, this is going to be a pretty quick lesson. In the past I have combined this with day one of this unit, but just because you're at home and things are moving a little bit differently, I decided to do it as two separate lessons. So I do have a first 5-minute question here. I would love for you to pause, um, solve the question, and then come back and check out if your answer is correct. Okay, so I'm assuming that you've paused, or hoping that you paused at least. So what we have to do first is we have to figure out how these two triangles are similar. So what I'm going to do, I'm just going to say triangle MNO is similar to, and now I'm going to figure out how they're similar. So this triangle has P, O, and Q. So first of all, we have to figure out which angle goes with M. Well, because we have these two parallel lines here, we have a Z pattern that goes like this. Up, over, and up. And you can see that angle Q is the same as angle M. So that means that angle M and angle Q go together. And in the next one in the first triangle is N, so we do the Z pattern again, and we see that it lines up with P. And all that's left is O. Okay, so now if we're going to solve for a side, we would write the lowercase letters for the side. So M over Q is equal to N over P is equal to O1 over O2. And again, I just label those so that I know which O I'm talking about, and we'll go from there. So now I'm going to plug in. So little m is actually side x. Little q across from side q is 4.4. Little n is 6.0. Little p is across from p, it's 4.0. And we could keep going here and write in the values for O1 and O2, but we don't actually have to because we have a complete ratio and we have a ratio with x. So now to solve for x, we just get rid of the 4.4. So we multiply by 4.4 on the top, on both sides. These cancel out. And x is 6.0 times 4.4. I think it was divided by 4.0. Yep, divided by 4. We get 6.6 centimeters. Okay, now as far as the scale factor goes, this is something I haven't really addressed much so far. So to get the scale factor, we just find two sides that are that go together, so like 6 and 4, and we just divide 6 by 4. So 6 divided by 4 is 1.5. And we could check it with this one that we found here, 6.6 divided by 4.4. We get 1.5 again. Or if we did it the other way, 4 divided by 6, we might get the scale factor as 0.6666. So I usually do the bigger triangle divided by the smaller triangle, and then I'll say the scale factor is 1.5, meaning that the bigger triangle is 1.5 times larger than the smaller. Okay, so that's your first 5-minute question. Now we'll move on to today's lesson, which again, it's really, really quick, and it might even be easier than lesson 1. So our knowledge of similar triangles helps us solve problems like optics, so camera lenses, eyeglasses, and it allows us to find the height of tall objects. So if we were at school, we would go outside today. If it were sunny, which I think it is, I'm doing it the day before, but it looks sunny tomorrow, which is too bad because we'd be out in the field, we'd measure the goal posts by using similar triangles, and we'd walk to the opera house and do that, and it would have been fun. But we can't measure those things directly, right? You can't run a tape measure up to the top of the goalpost outside, short of climbing it, which would be very dangerous and definitely not something you should try. So we use indirect measurement. So we measure it using mathematical principles without physically actually measuring it. So the first question here, it says a pole, so let's draw a pole, 3.8 meters high, casts a shadow that measures 1.3 meters. Okay, so this is the shadow. I'll just draw it like that so you know it's a shadow, and it's 1.3 meters. Now, first of all, we know this is a right angle. So let's do that for now. A nearby tree casts a shadow that's 7.8 meters long. Now, obviously, if the shadow of the tree is 7.8, it's going to be a lot bigger than this if its shadow is only 1.3. So then I'll draw the tree. Get some brown here. Really important that I have a brown trunk. I don't know why. I got this sweet tree. The tree casts a shadow, just like that. And we can say that this shadow is 7.8 meters long. And we could draw like a dotted line down here to represent the tree growing straight up. And that makes a right angle as well. So you might be wondering, well, how is this similar triangles? This whole unit's supposed to be called similar triangles. I'm going to label this H for height. Let me show you. If we connect these, and we connect these from the top of the tree to the edge of the shadow, we have actually created two similar triangles. And the reason that this is the case is because if you think about the sun and how far away it is, I think it's like 500 million kilometers or something. At any rate, it's super far. So the sun is really, really far away. And its rays come down to the Earth. And the idea is that if you're in one area, that the angle that the sun's rays make with any object is supposed to be exactly the same. Or at least so exactly the same that it doesn't really matter. And if you don't believe me, put two pencils on a table and put one a little bit further than the other. And then shine a light really, really close to them, like a flashlight or the light on your phone. And you'll find that depending on your angle, one shadow looks longer. And then start to move the light further and further back. And you'll find that the further away that light source gets, the closer the shadows become to the same. Now imagine moving that light source 500 million kilometers away or whatever it is. And at that point, the difference in the angle that the light hits is so fractional that we can just say that it's the same. So that means we say that this angle is the same as this angle. That's the angle that the sun makes with the object. They both have a right angle, and therefore the third angle is the same because angles always add up to 180. Okay, now let's solve the problem. So here we go. I'm going to take the values from this triangle and make them a ratio. I'm always going to do the letter on top because that makes life easier. So h over 7.8 equals, and then I set up the ratio with these in the same order, height over shadow. So 3.8 over 1.3, and now I'm ready to solve. I multiply by 7.8 on both sides. These cancel, and h is going to be 3.8 times 7.8 divided by 1.3. And we get 22.8 meters. And if we look at our diagram and if we think about it, this pole was longer than its shadow, almost 3 times. And this height is almost 3 times bigger than its shadow. So it totally makes sense. If I ask for the scale factor, we would do 7.8 divided by 1.3. It's 6. So the tree is 6 times taller than this. And so if we multiply 6 times 3.8, we get 22.8. So lots of little things you can do in there, but basically this right here that's the gist of it. All right, problem 2. Surveyors set up posts at points A, B, C, D, and E. They took measurements to calculate the width of the river. So they want to know this. I'll call it W for the width of the river. What is the width of the river? Well, first of all, we have to prove that we have similar triangles. We see two 90-degree angles, of course. So we have one angle that matches. And if we can get one more angle, like these opposite angles, we know we have similar triangles. And I always find it helpful to do this. Triangle ABC is similar to, so A, B, C. Angle A is the 90, so it's going to be D. And angle B is this one, and by Z pattern, it's going to be E. And they both share angle C. Okay, so that means A over D is equal to B over E is equal to C1 over C2, with this being triangle 1 and this being triangle 2. Now we plug in. Little a, we don't know. Little d, we don't know. So this ratio is useless. Little b is 50. Little e is 9. C1, that's what we're trying to find. We call it W for the width. And C2 is 13. So all that's left now, I'm going to write the W on the other side, just so it's a little easier to look at. We multiply by 13 on top. And we get 50 times 13 divided by 9. Approximately 72.2 meters across the river. And this is a good example where you can measure the width of something like a river. Maybe it's like rapids or something dangerous and you can't get across, or it's like a cliff to another cliff, like a gap between them, like a little canyon or something. So basically what you do here is you start here and you walk for 50 meters, and you place like a stake or a marker in the ground. Then you walk for 9, and then at a 90-degree angle or perpendicular to the river, you walk 13. Okay, and you make sure that you walk at 90-degree angles, and then you've created these similar triangles just like that. And you can use that to find this one here. Okay, so that's about it. And the only other thing you'd have to be careful of here, I guess, is that when you walk to this point and stop, you'd want to make sure that so you'd like mark a tree over there or something, and you need to make sure that the stake here, so imagine you put like a stick in the ground and there's a tree here, you would walk this way from the shore until you got to the point where you're in line with the stick and the tree. And if you've ever seen surveyors on the side of the road, they have these little sticks with like a camera in them, and they have another person further ahead or across a road or something. This is the type of thing they're doing, and using similar triangles or trigonometry is how they determine the size of different lots and where, you know, power lines would go or whatever. Okay, number 3, using mirrors. Again, we would have done this outside at school. It would have been pretty neat. So the law of reflection states the angle at which the light reflects off of the mirror is the same as the angle at which it hits the mirror. So all we're saying here is that this angle equals this angle. And if we imagine dropping a line from the top of the Eiffel Tower to the ground, we can say it makes a 90. Drop a line here and say it makes a 90. So now if we have two angles in a triangle that are the same, we know that the third angle has to be the same, and the triangles are similar. So you could actually use a mirror as well. And again, we would have done this at school, but unfortunately we can't. So this law of reflection is also useful in the game of pool, like billiards, if you're playing 8-ball or 9-ball. Clark and I do it in the garage a lot. We've got a pool table out there. And it's something that I've sort of mentioned to him, that if you want the ball to bank off the wall and into the pocket, you got to hit it at the same angle that you want it to leave. So let's go ahead and solve this. Summer's visiting Paris, blah, blah, blah. She places a mirror on the ground 500 meters. So that means that this distance is 500 meters. She then stands behind the mirror in such a spot that standing upright, she sees the top of the tower. So you can imagine she's looking in this mirror and she's seeing the very tippity top of the tower from her eyeball. Her friends, amazed at her mathematical approach, measure the distance from the spot where she is standing to the mirror, so from here to be 2.75 meters. And the important part here is the height of her eyes, right? So it's not going to be the height to the top of her head. It's going to be the height from her eyes, because that's where she's looking from, right? She doesn't have an eyeball on top of her head. And so her height here from her eyeball is 1.8 meters. And we want to find h. So it's very, very simple. H over 500. So object over, let's say, ground distance equals object, which is the height of the girl's eyes, over ground distance. And now we just multiply by what's underneath, just like before. So you can see here, like I said, today's nothing new really. I think it's actually a bit easier than what we've done before. And we get 1.8 times 500 divided by 2.75. 327.3, approximately 327.3 meters is the height of the Eiffel Tower, according to her investigation here. And obviously if you did this in real life, like if you were off by a little bit, in this distance here and this distance here, then you'd be off by a lot more here. So, you know, you just have to be careful with your measurements, and just know that if you're doing this in real life, it will be somewhat of an estimate, because there's lots of room for error. All right, last question before I give you some homework. A pinhole camera is used to take a photograph of a student who is 1.8 meters tall. The student stands 2.7 meters in front of the camera, and film is placed 10 centimeters or 0.10 meters, so watch out for units. That could be a trick, but in this case I've fixed it for you. Determine the height of the image. So first, we know that this angle is equal to this angle, and we know that if we draw a Z pattern here, because we can imagine this line and this line being parallel, So we go boom, boom, boom. So this angle is equal to this angle, and this angle here is equal to this angle here. So we know we have similar triangles, which is important. And now from here, we just set up our ratio. So we're looking for D. So let's do D over 0.10 equals. So I took the two values from this little triangle, and I got to make sure I set them up in the same way as this triangle here. Well, this is actually, should be pretty straightforward, because what we can actually do here is we can do this. So 1.8, 2.7, 0.10, and D. And so you can see the way this goes, right? The D goes with the 1.8. You can imagine flipping this triangle over, and the 0.10 goes with the 2.7. So equals, so D over 0.1 equals 1.8 over 2.7, and then we multiply by 0.10, and we get D equals 0.067 approximately is the height. And you can think about this way. Let's do 2.7 divided by 1.8. Oh, 1.5. And then if we do this divided by this, we should also get 1.5. 1.49. So we rounded, so we're good. All right, so that is the height of the image produced on the sensor of the camera. And your homework is not in this document for some reason, so let me pull it from here. Okay, so this will really be the end of similar triangles. In our next lesson tomorrow, we'll move on to trigonometry, sine, cos, and tan, and I think you'll really enjoy it. This is often the best unit for students in the course, and it'll be a nice way to finish the course. We should have another unit after, but I don't think we're going to have time. So make sure you're going through this stuff. Tell your friends to go through it. It's an easy unit. It's a nice way to finish off the year. And if you have any questions, as always, let me know. Okay, thanks, folks.